Okay, so let's continue our tour through some of the set operations. So we have now union, okay? The union of two sets, we write that as S union T, okay? It's a set that contains all the elements of S and all the elements of T. Could be in both, okay? And nothing else. So for example, we have, let's take a set like 1, 3, and 5, and another set 2, 3, and 5. And when I take the union of those, what I'll get is all the elements that are in both. So I'm going to have 1, or in either, I mean 1, 2, 3 happens to be in both, but that's okay. 5 is also in both, but that's okay. And so that's the result of the union. Okay, so that's how we say it in English, right? So again, let's try to turn this into a little bit more math. So here's a definition. S union T is actually equal to the set of all X such that X belongs to S or X belongs to T. Okay, I think of this as a very direct definition. Okay, and by direct, what I mean is this: I have equal, and I actually write down a set that is equal to. Right. So this is one of the ways that I can do a proof that has set union. I'll just simply start with the term that has a union, like A union B, and then I'll expand that into a set, and I'll just keep going. They're just full-blown equalities all the way through. Okay. Now it turns out that there's also another way to turn this into math, and this way, instead of thinking of the set, I'm going to think of the elements in the set. So what I'll say is that X belongs to the union. Okay, if and only if X belongs to S or X belongs to T. Okay. Now I want to make this clear. This is not a new definition. This is actually pretty much the same thing as what I had here, because this is an equality, right? So an equality, you know, tells us that X belongs to the first set, which is S union T, if and only if, right? X belongs to the second set, right? X belongs to the set of all X such that X belongs to S or X belongs to T. Okay. Now, what does it mean to belong to a set that's defined by a property? This is exactly the same as just the property. So X belongs to S or X belongs to T, right? So that's where this comes from. These two things actually say the same thing, but just from a different perspective. One of them actually works on the set at a time. The other one looks at the elements that could possibly be in those sets. The reason that I'm giving you two is because sometimes it's easier to do the proof from this approach, just the complete direct approach, and sometimes it's easier to do it from this approach, which is kind of a indirect that looks at the elements. So both are at our disposal, and as I just showed you, it's not that we have two different definitions, there's just two different ways of looking at the same definition. Okay, so let's see. So the intersection of two sets, and this is the way we write intersection, is a set that contains all the elements that are in both sets. So again, let's say that I have 1, 3, and 5, and I'm going to take the intersection of that with 2, 3, and 5. Okay, so I have the odd numbers and the primes between 1 and 5, and the intersection of that is going to be 3 and 5. Okay, because 3 is in both sets, 5 is in both sets, but notice that 1 is only in the first one, 2 is only in the second one. So this is the intersection. Okay. As before, I also want to be able to say this in a more formal language. Okay, so here is a direct definition. The set S intersect T is actually equal to the set of all X such that X belongs to S and X belongs to T. That's how we capture that notion of both sets. Okay, and as before, we also have a more indirect way of saying that, and it's basically opening up the equality definition. So for all possible elements X belongs to the intersection if and only if X belongs to S and X belongs to T. Okay, so again, those are two different ways that we have at our disposal to be able to do some proofs. Okay, all right. So what other kind of operations can we do on sets? Okay, let's try set difference. We have two sets, S and T. The difference of S and T, and we write it using kind of like just arithmetic minus notation. Okay, some authors actually prefer to write it like this with kind of a backslash. Okay, but S minus T is a set that contains all the elements that are in S but that are not in T. Okay, so let's see that I have 1, 3, 5. Okay, and I take away 2, 3, 5. And what I'm left with is simply the set that contains the element 1, because 1 is in the first element, in the first set, but it's not in the second set, so that makes it. Whereas 3 is in the second set, so we don't want that. 5 is in the second set, we don't want that. Okay. By the way, this is not a symmetric operation. In particular, 2, 3, 5, and I subtract 1, 3, 5. What I'll get is the set that contains 2. Okay. So union is symmetric, intersection is symmetric, set difference is not symmetric. Okay. All right. So so we have kind of the English or the intuitive way of saying what it means for S difference T. Let's say it in math. So S minus T is actually equal to the set of all X such that X belongs to S, but X does not belong to T. Okay. That's the direct definition. And a more indirect one, X belongs to S minus T if and only if X belongs to S and X does not belong to T. Okay, so great. So that's set difference. Now again, let's see what other operations we can have. And there's actually really only one remaining, and that's complement. And we write complement putting a vertical bar over the set. And what we mean is the set of all the elements that aren't in S. Okay. Okay. So for instance, and this actually gets a little tricky because let's take 1, 3, 5. Okay, so what is the complement of that? Everything that's not in S. Okay, so 2 is there, 4 is there. How about 6? We haven't seen 6 up to this point, so is that one of the elements that could possibly have been in that set? I don't know. Depends on what our domain of discourse is. Okay, so let's say that our domain of discourse is in fact all the integers. Then yeah, 6 should be there, 7 should be there, 8, and so on, right? But those aren't the only ones. 0 should be there, -1 should be there, -2 should be there, and so on. Right? The actual answer depends on what is it that we mean by the universe or the domain of discourse. That's one reason I feel just a little uncomfortable with complement. Okay, but anyway, let's put it in math, and it's just a set of all X, such that X does not belong to S, and we can say that X belongs to the complement if and only if X does not belong to S, right? Again, this quantifier here is crucial because that quantifier, the domain of discourse of that quantifier tells us what exactly should be in there, right? All the things that that I can think of but that are not there. Okay, all right. Just to really kind of emphasize that point. Okay, let's say S is the set of prime numbers, so 4 belongs to S complement. Yeah, I would say so, right? How about -4? I don't know. I mean, if we're talking about prime numbers, then the prime numbers are positive integers, so maybe I'm not even considering -4, so maybe that shouldn't belong to the complement. About 2.5. But if I'm talking about primes, I'm really not thinking about, you know, fractions or decimals, so probably that's not what I mean, right? How about pi? Oh my God, that's even a transcendental number. I'm almost certainly not considering numbers like that when I'm talking about primes, so maybe not. Fred's a nice guy and all, but if I'm talking about prime numbers, I'm not even thinking about Fred. My dog, oh, my dog is the cutest thing in the world. But again, if I'm talking about prime numbers, no, probably not something. The local group of galaxies, you know, that's like the biggest thing around here. But again, if I'm dealing with primes, that's not what I'm thinking of. So it's hard to actually say what's not in the set of prime numbers, what's the complement of the primes, because we're saying complement compared to what. And because of that ambiguity, I really don't like using complement. What I'll do is I'll be explicit. I mean T minus S, okay? Where T is exactly the domain of discourse, right? So it might be the integers, or the natural numbers, or the positive integers, or the reals, or whatever it is that I want to think of as the entire universe.